Welcome to Lecture 9. The last two lectures have built up some theory with the string, sum, and product lemmas. Today we'll see how to apply that theory to count compositions under various constraints. The example at the end of last lecture used the generating series for the set of all compositions to count the compositions of the integer 239. Now we'll turn to a related problem. Suppose I want to count the compositions of 239 where all the parts are odd. Just like the last example, we're going to use the string lemma to reduce this problem to a calculation of a coefficient. For this, we need to understand the generating series for the set of all compositions where every part is odd. To do this, we need to describe the set of all compositions in which every part is odd in terms of a simpler set. The set of all compositions is exactly the star of the set of positive integers. In the same way, the set of all compositions where every part is odd is exactly the star of the set of odd integers. So we let T be the set of odd positive integers and observe that the set of compositions we're interested in is equal to T star. We're going to be using the generating series for T itself in just a minute, so we'll compute it in advance. Phi T of x is simply the sum of x to the n over all odd positive integers n. That's a geometric series, which is equal to x over 1 minus x squared. By the usual magic of generating series, the number of compositions of 239 with odd parts is the same as the coefficient of x to the power of 239 in the generating series for T star. We can simplify that using the string lemma to an expression in terms of the generating series for T. We can substitute in the expression we have for this generating series, and a calculation gives that the coefficient we want is x to the 239 in 1 minus x squared over 1 minus x squared. Unfortunately, we're a little stuck here. We know using the geometric series and the negative binomial theorem how to pull coefficients out of certain series, and that's been enough so far. This series isn't one of them. We're now going to see a new trick that you can use to say something about the coefficients in a series like this. It won't be a formula, but it will give a way of computing the coefficient in principle. For now, let's forget that we were thinking about compositions and instead just focus on the problem of determining this coefficient. What we'll be doing actually determines all the coefficients at once, not just the one we're interested in. So we're going to give them all names. Say A0, A1, A2, and so on is the sequence of coefficients of 1 minus x squared over 1 minus x squared. We can eliminate the fractions by multiplying through by 1 minus x squared. This gives us an equation saying that 1 minus x squared is equal to 1 minus x squared times the series we're interested in. We then rearrange to collect like terms on the right-hand side, and then clean the right-hand side up using sigma notation. Looking at the equation we get here, we should take a moment to think about what we're actually doing. It might be your instinct to think of x as an unknown in this equation, but remember, in generating series, x is just punctuation. The real unknowns that we want to figure out are the coefficients ai on the right-hand side. This equation is a statement about two generating series. It's saying that the generating series on the left is the same as the one on the right. In other words, all the coefficients on the left are the same as all the coefficients on the right. In fact, you can think of this one equation as a system of infinitely many equations, one for each coefficient. The first equation says that the constant term on the left is equal to the constant term on the right, so 1 equals a0. The second equation says that 0, which is the linear term on the left, is equal to a1 minus a0, the linear term on the right. We get a similar equation for the coefficient of x squared, and the coefficient of x cubed, and so on. But from x cubed onwards, something nice happens, because the coefficient on the left is 0. So the equations for n at least 3 all just say that an minus 1 minus an minus 2 equals 0. Even though there are infinitely many equations here, we can do something that is essentially solving them. Solving the first 3 just gives that a0, a1, and a2 are all equal to 1. And then from 3 onwards, each term is the sum of the two previous terms. This is a recurrence relation that determines the entire sequence. And in practice, you can write the sequence out. You start with 1, 1, 1, and then each term is the sum of the two terms before it after that. This is essentially the Fibonacci sequence, only shifted one to the right. In fact, this problem is the same example that I gave you at the end of last week without too much explanation. In that example, I phrased it in terms of multisets because we hadn't talked about compositions yet, but it was essentially the same problem. What we've proved is that 1 minus x squared over 1 minus x squared is the sum of ANX to the n, where the sequence AN is determined by the first three terms being 1 and each term after the first three being the sum of the two previous ones. Have I really told you what all the coefficients are here? I would say that that's a matter of perspective. I've told you an explicit way to compute any coefficient you like, but I haven't exactly given you a formula. If we remember the problem we were actually trying to solve, what we wanted is the number of compositions of 239 where all the parts are odd. We saw that this is the coefficient of x to the 239 in this rational expression, and that's equal to A239, which is something like the 239th Fibonacci number, depending on where you think the Fibonacci sequence starts. Personally, I would call this a solution to this problem, but you might disagree with me. Thankfully, later in the course, we'll see a way that you can actually write down a formula in the more traditional sense for this number. I'll get to another example of counting compositions in just a second, but I wanted to give an interlude, which is a simple application of the product lemma that gives a surprising result. Here's a statement that is true about polynomials. It wouldn't be too hard to check, but it will be a little tedious. X to the 1 plus x squared and so on up to x to the 6 squares to make the series x squared plus 2x cubed plus 3x to the 4 and so on, where the coefficients go up from 1 to 6 and then back down to 1. If you think about how the coefficients in this huge polynomial arise, you can see that the coefficient of x to the n is simply the number of ways of writing n as the sum of two numbers from 1 to 6. And in fact, it's the same thing that happens if you think about the total that you get when you roll two dice. There are 6 ways of getting a 7, 4 ways of getting a 5, and so on, for exactly the same reason. When I say rolling two dice, I really mean two distinct dice, so a 3 then a 4 would be different from a 4 then a 3. What I've just observed here is really an example of the product lemma. If we wanted to set this up in terms of generating series, we would let S be the set of the 6 sides of a die, and the weight of a side be the number of dots on it. This is nice, but perhaps not super interesting. What is interesting is that in fact, there is a different way to write this degree 12 polynomial as the product of two smaller polynomials. Here it is. Thinking in terms of the product lemma and dice, what this other factorization is saying is that if you have two dice, where the numbers on the sides of the dice are the exponents in the first and second brackets respectively in this other factorization, then when you roll those two dice, you have the exact same chance of rolling each total as if you rolled two normal dice. These two strange dice that behave like a normal pair when you roll them together are called Sesherman dice. It's quite surprising that they exist, and very amusing that you can find them by factoring a big polynomial. Let's do another example of counting compositions. In the first example, we counted the compositions in which every part is odd. In this example, we're going to count the compositions where the number of parts is odd. There are different ways these questions can be phrased. In the last way, we asked for the number of compositions of a particular integer. In this example, we're asking for the generating series as a rational function, and also a formula for each coefficient. Since finding the generating series is part of the solution anyway, what we do is really no different. As usual, we're going to take the set of compositions that we're interested in and describe it in terms of simpler sets. Here it's the union of the set of compositions with one part, and the set of compositions with 3 parts, 5 parts, and so on. We haven't written S as the star of a simpler set, so we can't directly apply the string lemma. There actually is a way to make the string lemma work here, but we won't do that. We'll just apply the infinite sum lemma, since we've written S as the disjoint union of an infinite collection of sets. The infinite sum lemma tells us that the generating series for S is the sum of the generating series for all the sets we've written S as a union of. In this summation, I've indexed the odd numbers as 2n plus 1, where n ranges over all non-negative integers. And now we have the usual type of calculation. First, we use the product lemma to simplify each of the individual generating series appearing in this infinite sum. For each n, the generating series for the set of positive integers to the power of 2n plus 1 is equal to the generating series for the set of positive integers to the power of 2n plus 1. This is what the product lemma does. It turns Cartesian products of sets into products of polynomials. And now we do some simplifications. We use the geometric series twice. We first use it to describe the generating series for the set of positive integers as a single rational function, x over 1 minus x. We then observe that what we have is another geometric series, where the common ratio is x over 1 minus x all squared. And now we've written the whole thing as a single rational function. This answers the first part of the question we were asked. To get to a formula, we use the geometric series again, but in the opposite direction. Simplifying gives x plus the sum over all n at least 2 of 2 to the n minus 2 times x to the n. Now Bn was the number of compositions of n with an odd number of parts, which is equal to the coefficient of x to the n in this series. We've written the series in a way where it's easy to see what the coefficients are, so this gives a formula for Bn. Unlike the previous example, where our formula was a recursion, we had a nicer rational function here, and we were able to simplify it directly to obtain a direct formula for Bn. This week, we've seen the sum, product, and string lemmas. They tell us how, given a complicated set S, to write the generating series for S in terms of the generating series for simpler sets. It's almost like applying the product rule, chain rule, etc. to differentiate a complicated function in terms of simpler functions that you know how to differentiate. So far, we've seen how to apply these lemmas to problems that involve counting compositions. We did an example where there were no restrictions at all on the parts, but also we looked at examples where we had a restriction on the number of parts or on what the parts can be equal to. The two restrictions I looked at were first that the parts had to be odd, and second that the number of parts was odd. You can combine the different techniques I used to answer any number of related questions with all sorts of restrictions on the number of parts and what the parts look like. Whatever problem you're solving like this, what the techniques will give is a rational expression for the generating series. Then, if you want the answer to a counting problem, you just have to ask for a coefficient in that rational expression. We've seen that sometimes you can obtain a direct formula for that coefficient, and other times you can at least obtain a recurrence relation for the sequence of coefficients. Next week, we'll see how to apply these ideas, but to binary strings instead of compositions. The following week, we'll see what you can do with recurrence relations. Thank you for watching.